Okay, so first let's talk about the first exam that's coming up. Exam 1 is Wednesday, February 10th. And it's just going to be problems. And the way to, so here's how you know if you're ready. If it's going to be based on the approaches that you used in all of the assignment problems up through this Wednesday. So based on the assignments through Wednesday the 3rd. And they're not going to be identical, but they're going to be the same process, same thought process. So if you could get to the point on every one of those assignment problems where you could explain how to do it to someone else, you know why you made this decision here, this decision there, then you're ready for the test. And you can go to the bar. And if you are under 21 and you get to the bar, you have to wait till you're 21 to go in. All right. So, and all the solutions are posted up through up through last Friday. I just posted up through the last quiz. I guess I won't post the ones for like this Monday and Wednesday won't be posted till this Friday, but they'll be posted, so you'll have them for the weekend. And so if there are any that you've done, you haven't been sure about, or you haven't known how to do, the solutions are there. Yep.
We still have a homework assignment on at Wednesday at 2:10.
Yeah. Oh, yes, we will. That's. Oh, you mean that's due on?
No, like we have homework assigned each time.
Yes.
Already that one assigned when we have
Yeah.
the exam.
Mm-hmm. But the one that'll be assigned for like the Monday before is just going to be, there might be a couple of new problems, but it's mostly going to be just having you go back, look at another old assignment, make sure you understand those problems, review your notes, that kind of thing. Okay. Any questions about the test? There's one more thing I want to say about particle kinematics before we go on to particle kinetics. And that is circular versus spherical motion. Circular motion is motion confined to a plane where the object's moving stays a fixed distance from the center. So it stays a fixed distance from the center of rotation. Spherical motion, the only difference is it's not confined to a plane. It can move in all 3 dimensions, but it still remains a fixed distance from the center of rotation. So it's not confined to a plane. But it still stays a fixed distance from the center of rotation. in both cases, the velocity of a point is equal to omega cross r, and the acceleration of a point is the watermelon equation. So I just want to say, make a little table of what do omega and alpha mean when you go to spherical motion. So circular motion, just going to make this little table, spherical motion. This will be the variable. Okay, so first, omega, the angular velocity. In circular motion, that's always perpendicular to the plane. Normal to the plane of motion. So, you know, since we pretty much always use the xy plane when we're doing planar problems, omega only has a z component. In circular motion, the direction is the instantaneous axis of rotation, but it can be anywhere. You know, that can be changing over time. So you could get, well, I'll wait on that. And then alpha, the angular acceleration. In circular motion, that always has to be parallel to the angular velocity. In spherical motion, that doesn't have to be true, but you can think of it this way. You can break it up into a part that's parallel to the angular velocity, and this part determines whether the angular rotation is speeding up or slowing down. So let's say it makes the object speed up or slow down. And then second, there's a part that's perpendicular to the angular velocity. That's what you don't have in circular motion. And that's the part of the angular acceleration that makes the axis of rotation direction change. So causes changes in direction of the axis of rotation. But other than that, you can, mathematically you treat those two kinds of problems just the same. Any questions about that? We'll do some problems like that later on. Okay, so now we're done with particle kinematics. We're going on to particle kinetics. So what's kinetics? I know you heard these words before. I don't know why they have to make them so similar. You can do it using energy. Generally, though, kinetics just means that rather than just describing the motion based on what you could see in like a video or something, now we're dealing with the causes of motion. So we're going to introduce forces and the object's mass. When we get to rotational stuff, we're going to introduce moments, but we're not going to do that yet because these are particles, and so we don't make any distinction about different orientations. So now we're going to relate the causes of motion to the motion. Since particles don't have any orientation, we're not going to use the moment equation yet. So the only equation that we're going to use is Newton's second law. I'm going to always abbreviate that N2L. And it says add up all the, well, let me just write it first. So sum of F is equal to the mass times the acceleration of the center of mass. Okay, so this is the sum of all external forces acting on the object on the chosen object. This is the mass of the chosen object. And this is the acceleration of the center of mass of the chosen object. And the fact that these are only the external forces that we have to deal with is a very nice thing, because we're always going to be, I mean, even if you choose like a solid piece of metal or whatever, you can think of, there's like little atoms inside and they're interacting with each other and all this stuff, and we never have to worry about that kind of stuff. We only have to worry about what's happening to the boundary of the object as a whole. Anytime you use Newton's second law, you have to draw a free body diagram. That's a major point of emphasis for me. And so if you don't do that, you'll lose points, so just do it. So anytime you use Newton's second law, and later anytime you use the rotational equation too, the moment equation, I guess I called it, you need to draw a free body diagram of the chosen body. Okay, so free body diagrams. I'm going to abbreviate these FBD. So first, you need to draw a closed outline of the chosen body. So, for example, if your chosen body is a person, I don't know, maybe you don't have to do all the fingers. It's grimace. Okay, so that's a closed outline of the chosen body. This is not. And the reason that this is not as useful, and it's not allowed in this class, is that you're not being clear to yourself or to me about where the boundaries are. A stick figure doesn't have an outer surface. You know, this has an outer surface. I know that you're including the entire arm here. I'm like, you know, is this the bottom of the arm or the top of the arm? It just isn't. You're not being clear about where the boundary is, and where that boundary is really important. Okay. And that closed outline of the chosen body needs to have no internal details and no external objects included. Okay, so for example, if your free body is a car, that's a closed outline of the car. That's not what you want to draw for a free body diagram, because you have internal details. It's not clear if you're including the wheels, not including the wheels, including the windshield. It's not clear if you're including part of the ground, because there are external objects included, so don't do it like that. Okay? And second, include all forces acting on the object. This will also be couples when we talk about the rotational equation, the moment equation. And so there are two types of forces that we're going to be dealing with. The first type is forces where we know the direction. So if the direction of the force is known, then draw an arrow in the known direction. And associate that arrow with a scalar variable or value to indicate the magnitude of the vector. So a scalar is a number, not a vector. So for example, if there's the free body and you know there's a force acting like pulling on the front of the car, you draw an arrow in the known direction and associate it with, if you don't know the value, you give it a variable that's just a number, just a scalar variable. If you do know it, you can put 1,000 there, whatever it is. The second type is if you don't know the direction. So if the direction is unknown, draw 2 small arrows in the direction of the coordinate axes. Three of them in 3D. And associate these with a vector variable or a vector value. Vector or vector variable. So for example, if this is the free body and you know that there's a contact force between the tire and the ground, but you don't know what it is, you can write it like that. Free body diagrams have to account for every force on the object. So how do you know if you've accounted for all of them? How do you know you haven't missed any? They won't in dynamics necessarily. Yeah. You're right about that. The problem is, like if you have variables in there, that won't tell you whether you've missed any or not, because if you have variables in there, you can solve for those variables whether you have all the forces in or not. You just get the wrong answers. So here's how to do it. These external forces only arise 2 ways. The first is body forces. Actually, instead of body forces, let's call those force fields. Makes us feel more like we're in a comic book. Usually for us, that's only gravity. That's usually just the weight. But it could include magnetic fields and electric fields. I don't think I have any problems in this class that talk about either of those, but it could be. dot, dot, dot. I don't know. There's probably a lot of other types. And so those are easy. Like, basically, to make sure that you haven't forgotten the force fields, mainly you're just going to say, have I drawn a weight vector in there? That's all you're going to do. Then the second thing, what about all the only other type of force is contact forces. And so you just need to go mentally around the outside of the boundary of the chosen object and just look for places where there's contact. So go around the boundary of the chosen object. Mentally, anywhere there's contact, there's a force. Otherwise, there's no way there can be a contact force. So anywhere the outside world makes contact with the boundary, there's a force. And so when these problems get complicated, I think this is a nice way to kind of center yourself. Like when you get problems where there's a ton of forces and it's really easy to just sort of look at it and be sort of overwhelmed, just remember, okay, well, put the weight in, and then just go around the boundary. Anywhere there's contact, you have to deal with that with some kind of force. Once you've done that, then you have everything. Okay. Okay, so here's an example. Okay, so let's say that, so there's some mud here and then like a ramp. Let's say this truck is stuck in the mud. Like a flatbed truck. And okay, the owner's trying to push it out. That's what caused this problem. You can tell he's working hard because of the sweat. My new F-150. Why is my head so big? Oh, so it's easier. Might be sticky mud, though.
Might be a sinkhole.
Yeah. He's wearing clothes. Okay, and okay, so in the back, it's not just the F-150. His pig is in the back. And let's say his pet crane is standing on top of his pig. And let's say that there's a helicopter that for some reason, like, they don't want him to get his truck out. So they like have a cable attached to him and they're like pulling on him. Okay, so let's say that's all that's going on. He's taking it a little too hard, but it's especially weird about the helicopter thing. I'd feel a little frustrated if I was trying to push my truck out and that was happening. But okay, so let's draw a free body diagram of the truck, and second, a free body diagram of the pig. Okay, so the idea of this is there are a million things going on. It's easy to just look at it and get sort of overwhelmed by it. And let's just be disciplined about it. And for everything we isolate, we're going to apply the weight force, and then we're going to just mentally go around the boundary looking for contact. And if you do that, it makes that job easy. So for the truck, okay, so there's the truck. We know there's a weight force. mg acting down. And so that's all the force fields. And now we're just going to go around the boundary. There's contact with the rear wheel. So I don't know, let's just say that's a normal force, R. What these forces actually are, do we know the direction, do we not, do we know the value? That can be a trickier thing, and we'll talk about how to do that for different types of joints. But as far as knowing whether you've treated all the forces, that's the thing that you can just be systematic about. So the force on the mud, I'd say that's probably a force with an unknown direction. Let's call that reaction force mud, RM. And then over here, the owner is applying this force, F sub O, force by owner. And then in the back, there is an unknown force applied by the pig. There's nothing else along the boundary, so there's nothing else going on. There are other things. I mean, if that crane wasn't standing on the pig, this force would change. If that helicopter wasn't pulling on the owner, that force would change. But those don't directly come into this. All you have in that free body diagram are the interactions between the after the weight, all you have are the interactions between the boundary and whatever is touching the boundary. Okay. Yep.
Would FO be represented as scalar there?
Yes. Yes. Thank you. That should be. Yep. You're right. Friction. If there's no friction, I don't know. I don't know much about pig's claws. About pig talons, but yeah, if you're going to neglect the friction, then it would be just a downward force. If you're going to include the friction, it would be an unknown direction. Okay, so now, well, any other questions about this one? So now the force on the pig, free body diagram of the pig. You don't have to get all worked up about getting the outline right, like I'm doing. Okay, that's the outline of the pig. So there's the weight. And then on the pig's feet, I'm lumping both of these contact forces into one, but I'll call that the force applied by the truck. So that's contact down at the feet. Keep going around the boundary and you get to the crane. And so that's the force applied by the crane. Keep going around the boundary and there's nothing else. So there's no direct contact between the owner or the helicopter or the mud. So this is it.
You have to put a form vector on the front feet to consider.
Yeah, so if you, for particles, since where a force is applied doesn't affect anything because we're treating it like everything is acting at a point, you can always lump things together. If once we get to rigid bodies where we're dealing with changes of orientation, the way it's broken up into the front and back does matter. Now, there's a notation thing that's going to be important. I'm going to call it the subscript notation. For force. We'll also use it for couples later. Vectors. Don't use this for scalars, and I'll explain why in a little bit. But you'll get wrong answers if you use this for scalars. If you use this for forces with known directions, where you're associating those arrows with scalar variables, doing this will give you wrong answers. So don't use this with scalar variables associated with known directions. Okay, so the subscript notation says the force AB is the force on A by B. So the first subscript is the one that you're acting on. The second subscript the first subscript is the body that receives the force. The second subscript is the body that applies the force. So going back to the truck example, for the free body diagram of the truck, we know the direction of the weight, so we're not going to use the subscript notation for that. We knew the direction of the force applied to the truck by the solid ground, so we're not going to use it for that. But that force applied by the mud, we didn't know the direction. So I'm going to write that as the force on the truck by the mud. And then this one we did know, what did I call that? FO. And then the force applied by the pig, we didn't know that direction. So that's the force on the truck by the pig. And one thing that you notice, I mean, by the way these subscripts are set up, is the body that you isolate is always the first subscript of any of these forces, right? Because our free body diagram is only deals with the forces on the chosen body, you know. So these are the forces on the truck. Free body diagram of the pig. We had those two unknown forces. He's gotten a little fatter since last time. So the weight, we don't use that, but we do have the force on the pig by the truck, and we do have the force on the pig by the crane. And the real benefit of this subscript notation is how easy it makes Newton's third law to use. So Newton's third law comes up in this case. It's the relationship between the force on the truck by the pig and the force on the pig by the truck. Okay. So Newton's third law. And I'm going to always abbreviate that N3L. That's the one that says every action has an equal and opposite reaction. That could not be a more confusing way to describe this law. We're going to do it in two ways. So if you have forces with a known direction, and so say these are contact forces with a known direction. When you go to the other body, the other contacting body, the variable stays the same. And the arrow switches directions. So, for example, if you have these two objects in contact with each other, say this is body A and this is body B, a free body diagram of A looks like this. And a free body diagram of B looks like this. The arrow is opposite, but the scalar associated with it is the same. And then second, if the force is an unknown direction, FAB is equal to negative FBA. So if you switch the subscripts, you switch the signs. So for example, if you have these two objects connected by a pin joint, say that's body 1 and that's body 2. A free body diagram of body 1 looks like this. It's the force on 1 by 2. And then a free body diagram of 2 that is the force on 2 by 1, and Newton's third law says that's equal to negative F12. And in all cases, whether you know the direction of the force or you don't know it, the reason that you use Newton's third law is because it cuts down on the number of variables you need to represent a system. So, you know, you're always in this battle between the number of equations you have, that's your information, and the number of variables you have, that's the stuff you don't know and you want to find. And so using Newton's third law this way lets you reduce the number of variables that you would have by 2. If you know the direction, it lets you reduce the number by 1. But it gives you a chance for the number of equations to catch up to the number of variables. Any questions about any of those? Okay, let's stop there, and I'll do an example next time.